Okay, so we're going to go on. Our next speaker is Ahmed Almheiri. And this is a great occasion in a way, since this is our first speaker from Abu Dhabi. And I hope this is heralds a new era in scientific cooperation in the Middle East. Ahmed has big plans for Abu Dhabi.
Inshallah.
Sorry?
Inshallah.
Yeah. Inshallah, indeed. And we are all looking forward to it. And Ahmed's lectures. So Ahmed is someone I know very well, since he was a student at Santa Barbara, a student of the late beloved Joe Paczynski, and you all know of his incredible contributions over the last few years to the black hole information paradox, which is what he's going to be talking about today. So, no further introduction.
Thanks, David. Okay. Thanks again, David, and to organizers for inviting me to be here. These past few years have been very interesting. Yeah. Is it better now? Better now? No?
That's a good beard.
To my beard. I see. What about now?
It's not worse.
It's not. Did it increase the sensitivity or something? What about now? No, it's working, but maybe raise the volume. Testing, 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 testing. Testing. Okay. Okay, I'll try to speak up. Okay. What I was saying was, so thanks, and these past few years have been very, very interesting. There have been a lot of progress towards resolving many paradoxes. One of which David just mentioned, the thing that allowed me to be here. And something else is more about physics. It's about black holes. My lectures is going to be focused on two topics. The first, roughly 3 lectures, are going to be about the black hole information paradox. And at the end, I'm going to mention some recent work that I have not published in yet, but I think it's an exciting topic, and it might be useful for the young generation to pick up on the tools early. Okay.
Explain the title.
Oh, it's the double-scaled SYK, a certain limit of the SYK model that many of you might be familiar with, and how there exists a set of rewriting. There's a rewriting of the theory which you can associate with the bulk dual of double-scale SYK, which you can assign a Hilbert space. And the amazing thing about this story is that the bulk space-time can be seen to emerge from a more fundamental and discrete structure. Okay, and we'll get into all of that in a few days. Okay.
That connection, you notice that Micha Berkowitz is going to give a talk on core theory.
When?
And because of our problem, we will actually try to maybe reschedule it before your last talk,
Okay.
because that would help, right?
Yes, yes, yes. Although maybe it might actually might be more helpful for me to talk before Berkeley's.
I see.
Yes, because I'm going to go very, very basic, and people might be able to follow more from Berkeley's more recent results, maybe. Yeah.
Because he actually was scheduled for the last day. So you say
It makes
more
sense for me to speak first.
Okay.
Yeah. Okay. All right. So we're going to focus on the black hole information paradox. And in these lectures, what I'm going to try to do is convince you that it's no longer a paradox. Okay? Instead, what we have is that it's been demoted to a problem. Okay? The original thing that was called a paradox, I will show you where the wrong assumption was made, and we can point to exactly what quote unquote Hawking's mistake was. Okay? And this is science. There's no shame. Okay. Okay.
Possible to explain his mistake in 2 sentences to begin with?
There are non-perturbative effects that he forgot to take into account. Okay, let's see. And the reason why I say it's a problem is that it's not just, I'm not just erasing the first line entirely, is that there are still some open questions about understanding sort of, let me just say for now, the microscopic details for how black holes evaporate and so on. It's the route that Hawking took to compute to analyze black holes is you first, so you show that black holes evaporate, the black hole transforms from a black hole to radiation. He computes the quantum state of the radiation, and then computes the entropy of that quantum state, and you get a wrong answer. The recent results shows you that you can compute the entropy without going through that middle step. Okay? It's kind of surprising that you can compute the entropy of the radiation without first computing the quantum state. And if you do that carefully, you get a different answer from what Hawking found. But maybe I'm jumping the gun. So let's just go slow. Okay, so while I'm in the middle of corrupting your minds, let's begin with so-called central dogma of black holes. The central dogma is the statement that, as seen from the outside, a black hole behaves like a quantum system, a standard quantum system, with area of the horizon over 4 g Newton, number of degrees of freedom. Okay? And it evolves unitarily under time evolution. Okay? So you can draw the following picture, that from the outside, here's my black hole. If you draw sort of a radius around it, and you only do observations from the outside here, it's the same thing as some a over 4g number of, let's say, qubits interacting with some Hamiltonian, and you won't be able to tell the difference. My lectures are going to be about justifying this replacement, at least from the perspective of quantum information, as in for just one set of probes. The upshot is that the statement is that this claim results from treating the gravitational path integral carefully. So I'm going to talk, so here's the path integral. So z is a function of metric and some fields. dg, df, e to the minus s, g comma f. And so it results from just defining the theory in this way and treating this path integral carefully. Okay. Now, what I'm going to do is I'm not going to discuss the subject in sort of all generality. I'm going to consider this at least what I find to be the simplest possible model where we can find where we can find the Hawking's paradox, or construct Hawking's paradox, and then proceed to resolve it. So, okay, now I'm going to make a claim. So the claim is that, well, the art of being a good theoretical physicist is to be able to find sort of the simplest possible model, but without compromising on the effect that you're trying to analyze. Okay? And for us, we're going to look at gravity in 2 dimensions. Okay? Yes, gravity in 2 dimensions is very different from gravity in higher dimensions. 2 dimensions, you don't have propagating gravitons. But nevertheless, we are going to recover the same important features for the information problem. So we're going to consider 2 dimensions. Let me erase this. Model is going to be dilaton gravity. Of Jakiv-Teitelbaum. I'm not going to attempt to spell that. Just JT coupled to a CFT in 2 dimensions.
I'm sorry, can I ask a question?
Please.
About what we raised related to what you write now. So what you wrote previously, I believe, would be perhaps well-defined for the model that you are going to discuss now, but it's not well-defined in real black holes. So when you said have treat Keltner or whatever this thing, by this thing you must have added something to it. So what precisely do you have in mind for 4 dimensions?
Yeah. Surprising thing is that the things I'm going to talk about are they're not going to care about the UV cutoff. They're not going to care about UV physics. There are IR effects that are going to well, the physics, the new physics that we need. You put whatever cutoff you want. Yeah. Okay. So my action is going to be the following. So I'm going to use I for action because S is saved for entropy. So I'm going to have IJT of phi and metric plus a 1 plus 1 dimensional CFT that couples only to the metric. As in it's a CFT with background metric G. And I'm going to keep this general. So what I'm going to say is going to apply for any conformal field theory. This action, however, is given by the following. So Ricci scalar plus here so M2 is a two-dimensional manifold with a boundary plus minus phi is the dilaton. It has a constant piece, phi naught. And here this phi is dynamical. And phi b is the boundary limit of phi.
Which is constant?
Say that again.
Which is constant?
Phi naught is constant.
And phi b also.
Say that again.
And phi b, phi the boundary.
Oh, correct. Yes. This is constant. This is constant. It doesn't have to be. You can choose what you want. But you can always find a gauge in which it's constant. This is M2, boundary M2. This thing here, this term in the this first term in the action, is purely topological, okay? And it's just given by 2 pi times chi, the Euler character of the manifold, which is just given by 2 minus 2g minus b, the genus, and the number of boundaries. Okay. Okay. So we said this is general.
So
Yes?
you think of that as something that happens in the bulk and something that happens in the boundary?
Right now, this is a bulk gravitational action, and it has boundary terms.
No,
Need-
but the CFT part.
Oh, the CFT here is a bulk CFT. It has nothing to do with the dual CFT living on the boundary. Okay, so I have, in the bulk, I have gravity coupled to matter, and I'm considering the special case of matter being a conformal field theory, just for technical simplicity. Yes?
Can you explain what
K? K is the extrinsic curvature that you need to add in order to have a well-defined variational principle in the bulk. Okay. Now, since we have a boundary, we need to specify boundary conditions. So,
Just one second.
Yes?
What is the relation between phi naught and phi b?
okay. So, there's something you can call the dilaton, which is phi naught plus. Oh, sorry, you said the difference between phi and phi b?
No, phi b and the first term has a phi
And phi naught?
Yeah.
Okay. So, let's see.
I mean, this
Let-
phi is the bulk field, right? This phi type.
Let me say it this way. First, so we have a dilaton, which is the sum of phi naught and phi. Okay? This phi has a boundary, has some boundary value. We're imposing some boundary conditions, which is that this is equal to, so at the boundary is phi naught plus phi b. Okay? So this is part of the boundary conditions. Another, or let me say it here, I'm going to ignore phi naught. Okay? So the boundary conditions are that phi near the boundary goes as phi b, which goes as phi r over epsilon. Phi r here is sometimes called the renormalized value of the dilaton, of the dilaton. Epsilon is the distance from the boundary. So here, so I have a disk. Maybe draw here. Here's my disk. And here we're imposing that what we mean here by boundary M2 is that we're cutting out a circle out of the disk. It doesn't have to be a perfect circle. It's some general boundary curve. And the distance here, roughly speaking, is epsilon. Okay, let's just think of it like that for now.
And you're working in Euclidean
I'm working in Euclidean, yes. Well, currently. For this picture, it's Euclidean, but you can do everything also in Lorentzian. In fact, most of my time I'm going to be in Lorentzian space. Also, there is the boundary condition on the metric. Actually, maybe I should have started with this, because then the epsilon would have made more sense. The metric, we want to consider metrics that are asymptotically ADS. This means that G UU goes as 1 over epsilon squared as epsilon goes to 0. Okay. So for those that are familiar with, let's say, the ADS2 in Poincare coordinates, for example. So there we write down minus dt squared plus dz squared over z squared. Z is the coordinate from the boundary. As z goes to 0, or rather when z is very small, when z is equal to epsilon, which is very small, this thing goes as 1 over epsilon squared. Okay. Okay. So what is nice about this model? It's the fact that by performing the phi integral in the path integral, we can completely localize the metric to be ADS2. Because that's just because when you integrate phi, you get a delta function. Let me just say that again. So in the path integral, we have the following contribution. So the path integral includes integral over phi, e the integral phi r plus 2, plus other terms. If you do this integral for phi on a contour that is parallel to the imaginary phi axis, then this is a delta function r plus 2. Okay? And what I mean by this delta function, it's a delta function at all points in space-time. Okay, good.
We're allowed to choose any contour we want?
In principle, I don't know what the right guiding principle is to choose the right contour. But for now, I'm going to define my theory as choosing this contour. Okay. Let's see. Okay. So we just have ADS2. From this action, so we can get before we fix the metric to be ADS2, we can vary with respect to the metric and get Einstein's equations. So if you consider di, dg, mu nu, then you get that some differential operator acting on phi is equal to the stress energy tensor coming from the CFT part of the relation, where this is the stress energy tensor on ADS2, because we said we have this delta function. And this differential operator also depends on the metric, which is ADS2. It's not important what exactly this differential operator is. Okay. Now, we are interested in...
You got this result just because you decided not to copy the control of field theory also to the field, right?
Exactly, exactly.
If you incorporate also such a coupling, then the whole story will be different.
Correct. well, one thing, so it depends how you couple the dilettante to the matter. This is going to get much more complicated. We're not going to get the simplification with phi couples to the CFD. And here we just want to consider the simplest case possible. Any other questions? Okay, so we are interested in black hole solutions. And although it might sound crazy, we want evaporating black holes. The only solutions in this theory, actually I take that back. These are not the only solutions, but the solutions we're going to consider are eternal black holes. So black holes that, at least naively, are not evaporating. Those are going to be vacuum solutions of this theory. Vacuum solutions means that the expectation value of T mu nu is equal to 0. So vacuum solution. T mu nu, radius 2 is equal to 0, which are eternal black holes. And let me draw these solutions or these spacetimes. Now I'm in the Lorentzian signature. Here's my ADS2. The boundary that we were talking about, where we impose the boundary conditions, phi equals phi b, and the metric goes as 1 over epsilon squared, is somewhere like this. There are two boundaries. It's an eternal black hole, which, well, AKA a wormhole. Let me write down now what the solution is. The metric is something like this. These formulas are going to be important for, well, they're going to be important later. That's why I'm showing all the details. And so that's the metric. You might be a little bit confused because we said that the spacetime is ADS2. You can show that by coordinate transformation, you can take this to the standard, let's say, Poincare coordinates, okay? Which I'm going to write down actually in a bit. The dilettante looks like this. Okay. So lines of constant dilettante are lines like that.
I'm sorry,
Yep.
what is the singularity?
Excellent question. In this theory, it's not clear that there's a singularity. It's not. The question is like, well, how about this? There's no curvature singularity. It depends. You might say that the singularity is where phi goes to 0, for example, or where phi goes to minus infinity. Well, phi equals 0 is some line here, but it's not obvious that anything goes wrong in the theory when phi goes to 0. But when phi goes to minus infinity, there is now, remember we said that the dilettante is really phi 0 plus phi. Maybe it seems like the best candidate for singularity is when phi is equal to minus phi 0. Okay, you can maybe that's You might want to call that a singularity.
Why is there a reason to expect that this describe anything that has to do with generic flavorless?
This black hole, we'll see, well, the short answer is that the results that you get out of this, they check a lot of boxes. Okay? Like it satisfies the central dogma in a very surprising accuracy. Or let me say it this way. Maybe this black hole is this black hole is not like real black holes, but understanding this kind of black holes might be a step to understanding more realistic black holes. So let me we can come back to this after we see the.
Where does that vanish?
So let's take, before I answer that, phi naught, remember the coefficient of phi naught was this Euler character term. This means that phi naught controls the topological expansion of the theory. So if we in what I'm saying, we're going to, at least for the moment, focus on the disk, which means we want to suppress higher topology. Suppressing higher topology means taking phi naught to be very large. If phi naught is very large, so now we need to take phi to be very large and negative. That's somewhere here. Okay.
I'm not clear coming up to please explain what the diagram means. I don't
Okay, let me.
I didn't know, sir.
Thank you for asking that question. So I was getting ahead of myself. I didn't label the coordinates on this diagram. So in this diagram, these are lines of constant sigma. Same thing with this. Lines of constant u look like this. We are defining our boundary to be well, this line and this line, which means that these dotted lines are the event horizons of the black hole. Okay? So we have this black hole is really a wormhole. It has two exteriors. This is one exterior region, and this is the other exterior region. JT gravity, we know in some limit, or rather JT gravity is dual to SYK in some limit. So this physics of this space-time can be thought of as the physics of two SYK systems, one living here and the other one living there. Okay, hope that. Okay, so lines of constant phi are these lines here. It stays, it's positive, well, it's positive up until some line here, where phi is equal to 0. And then it becomes negative, and it's equal to minus phi naught somewhere up here. This space-time, if I didn't tell you where it came from, you would say that it's the conformal diagram of a ADS Reisner-Nordstrom black hole. In fact, the JT gravity, at least from the perspective of the physics outside, is really very, very close to the physics of the near horizon region of a ADS near extreme of black hole in higher dimensions. Okay. Thank you. So beta, so far, is just a parameter of, what was the question? Yeah, it's just a parameter. So this is a one parameter family of solutions parameterized by beta. Ultimately, beta is, well, it's related to the mass of this black hole, the energy as measured at infinity. The energy is going to go as 1 over beta squared, roughly speaking. Okay. Right, so these things here, or rather this coordinate system, I'm going to call the black hole exterior coordinates. Okay? We can choose to describe the same physics in a different coordinate system, which is the Poincare coordinate system. Which is given by this. So ds squared is minus dt squared plus dz squared over z squared. And phi is equal to 2 pi r, 1 minus pi over beta squared. Oh, I just changed coordinates. Let me do this. X plus x minus over x plus minus x minus, where x plus minus is equal to t plus minus z. The metric in these light cone coordinates is given by this. Okay. So this describes the same physics, but it covers a different patch of the space-time. So here are the horizons. Here are the horizons of the black hole. These coordinates, they cover a patch looking like this. Okay? Where this point here is z equals infinity. This is lines of constant z, and time runs upwards here, or t runs upwards. It's going to be useful for us to know the coordinate transformation between these two coordinate systems. But before we do that, we can write this in terms of light cone coordinates, and it's going to be 4 pi squared over beta squared dy plus dy minus times sine hyperbolic squared pi over beta y plus minus y minus. Okay. Where y plus minus is u plus minus sigma. The transformation between these y's and these x's is the following. Pi over beta, tan hyperbolic of pi over beta, y plus minus. Okay? So we're still in the setup stage. And I'm going to do one final piece of construction, say. I want to include, in addition to this black hole, I'm going to include extra regions external to the black hole that the black hole can evaporate into. Okay, so here's our black hole. Okay, here we have ADS2. I'm going to introduce or rather, let me erase this first. Let's consider a two-dimensional half space. Okay? So this is two-dimensional flat half space. Okay? I've imposed that it's flat space. And let's say that here I don't have gravity. All I have is a CFD living on this flat space. So I have just CFD on Minkowski, no, I shouldn't use M, G flat. Okay? Now what I'm going to do is I'm going to glue this half space onto my bulk theory along the boundary. Okay? So this means that the CFT here can now talk to the CFT here, but the gravity here is restricted to this region. So the picture I'm going to draw is the following. This is a hybrid system. So here I have gravity plus CFT, while here I just have CFT, and here also CFT. Okay, so I have two copies of this flat space region, which I've coupled to the two boundaries. And I'm going to make more precise what I mean by coupled and so on. I'm going to label this half here by BR, meaning the right bath.
By gravity plus CFT, the gravity is fixed for areas too, except near the boundary.
Correct.
So you really need the boundary.
Correct, but I didn't want to get into the boundary degree of freedom. I will talk about that later. Here I just mean that it's given by the JT action that I wrote down. But there's no action for the metric here.
No.
Question?
And the safety on the two sides affect the safety in the middle and
Yes,
change
yes.
the gravity inside.
Yes, they can, and I'm going to talk about that. So let's see. So this thing here, I'm going to label by BL, and I will call the left bath. Yep.
You think about things in the right, in the left, as the safety rules, whatever happens
No.
inside?
No,
It's not.
it's not. It has nothing to do with that.
Just to get it right, once you fix the ADS metric, you're not relying on dynamic derivative.
Correct. So let me see. Gravity for now. But there is actually there is some dynamical physics, which is the dynamics of where the boundary is. But the physics of that is not relevant is not important for my talk, and so I'm going to disregard it for now.
But before you discuss the boundary conditions,
Uh-huh.
now you have the CFT in this triangle.
Uh-huh.
It's also boundary conditions.
For the
It
CFT.
looks like they share a boundary.
Correct. It looks like they share a boundary, and so you let me just say it this way, that I'm going to continue to impose Dirichlet conditions on the metric. The fact that on the metric and dilettante, the metric goes as 1 over epsilon squared, and the dilettante goes as phi b. But for the CFT, I'm going to impose transparent boundary conditions. Okay? And what that means will come up in a second.
But then
Yes?
you're going to show that that's consistent with this, there being one boundary.
There being one boundary.
Well, when you glue things together,
Yes?
you think you're gluing one boundary to another boundary, so there's only one curve there.
Yeah. There's still only just one curve there.
And that's the boundary of the CFT as well.
Oh, I see what you mean. Okay. Yes, more precisely, these two are glued along this curve.
Yeah.
Yes.
So it's not along the straight.
Correct, but I'm taking epsilon goes to 0, and so it doesn't really matter.
They're taking epsilon goes to 0, so it only matters for epsilon. But that's the dynamic of boundary.
Correct. So, but I'm going to consider a static state. The state of the system we're going to consider.
So is it only for such states that it makes sense to go?
No. People have considered states that have non-trivial time evolution, and you have to keep track of how this boundary particle changes as a function of time, how it responds to the stress energy coming in from the bath CFD. So you can do all of that.
So it's kind of a,
In principle, yeah, I don't see why not. I don't think it's, no, I don't think it plays a role. Like, because you can take n equals 4 super Yang Mills and couple it to something else. That has an interpretation of ADS5 or whatever being coupled to something else.
So is the curvature discontinuous? The Ricci curvature is discontinuous when you cross the boundary?
Yeah.
And the stress energy tensor, I don't understand how.
Let me write down the, what do I mean by transparent boundary conditions? Maybe I can write it here. Let's see.
Move the board.
Sorry? Move the board? No, this is just small. Let me first. Okay. Let me first say that, so we already said that they're joined at epsilon. The metric here, I said it's flat, but more precisely, I mean that it's equal to this. Minus ui minus ui plus over epsilon squared. So the metric here, if you take it to be very close to the boundary, you'll get this. Okay, so I'm saying that the metric is continuous. Okay. But the curvature has a discontinuity. Right? The curvature is -2 here and then 0. Eventually what this means is that there's a localized delta function of energy right here. And you can imagine that if you do this transition a bit more smoothly, that you can regulate this the delta function singularity at the boundary. But it really just stays there. So when we do this, what it means is that bath time is identified with external black hole time. Okay? So the time that runs up like that just continues. You can just keep drawing these slices like that. And slices of constant time look like this. Okay? And okay, now what do I mean by transparent boundary conditions? Let's see. Okay. So recall that no, actually, let me come back to that later. Okay, let me come back to that later. So far, so this spacetime that we constructed here looks very similar to something else that you might be familiar with. This looks like an eternal black hole in asymptotically flat space. Right? If I was to erase this line and this line, this is the conformal diagram for just Schwarzschild in higher dimensions. If I put the singularity here, then it's like the conformal diagram of eternal Reiser and Ostrom in asymptotically flat space. And now so you should you can take this model to be this model with the flat space regions as a toy model for a flat space Reisner-Nordstrom black hole. Okay, before I talk about
construct this, you need to put in an external energy management or.
yes, you do.
Did you say that somehow natural can be traded for some kind of charge that creates a.
No, yeah, I don't know what the exact relation is between that and the charge of the black hole. Yeah, but I guess there must be some relation.
Another question, if you think about the dual description of this, you said that before you put in the heat bath, you have two SYKs.
Yes?
Correct. And what is the heat bath corresponds to coupling each separate SYK to the heat bath?
Yes. The dual picture looks like this. You have SYKs, two SYKs, a left and a right, and you've coupled them to these quantum wire. Okay? So, or this, yeah, this one-dimensional quantum system. Okay?
Sorry,
So far the system was without electromagnetism, so how suddenly you got to charge it with this This is going.
Sorry.
Oh, that's
I didn't get charged. It's just an observation that, well, actually, let me say two things. Well, first, it's just an observation so far that this conformal diagram looks very similar to a conformal diagram of a Reisner-Nordstrom. Okay? Now, the other comment is that if you start with Reisner-Nordstrom, true Reisner-Nordstrom, and look at the near horizon limit, there is some relation between the charge of Reisner-Nordstrom and the boundary value of the dilaton and things like that. Okay, so there's yeah.
You're going to use this observation.
No, this is just to motivate that this model might have some relation.
Is it toy for any Reisner-Nordstrom or just an extreme?
It's near extremal.
Near?
Yes,
What's the?
it's definitely not extremal.
What's the parameter that creates
Beta.
extremality?
The fact that beta is not infinity. Okay, actually, let me talk about the stress tensor now. Okay, so we have a CFD, and so we have holomorphic factorization. Which means that the stress tensor factorizes into left movers and right movers. There's T y plus, which is a function of only of y plus, and T y minus, which is a function only of y minus.
This is because why?
This is because it's a conformal, exactly, it's a conformal field theory in 2 dimensions. So here we have a CFD on flat space, and here we have a CFD on curved space. There's a relation between the stress tensor, the CFD on curved space, and that on flat space. In particular, that you can find that there's a definite way in which the stress tensor depends on introducing a conformal factor to your metric. Okay, so under a Weil transformation, which is, let's say, the following one, we have some ds squared of some of g. Let's say it's equal to minus omega squared of times ds squared of eta, then the stress tensor, say t plus plus, g is equal to t minus minus eta minus so-called conformal anomaly term. Okay? Where C here is the central charge. Okay, that's C over 12 pi. Oh, thank you. Oh my, yeah, thank you, T plus plus. Beta. Exactly. So this is what happens when you have a Weyl transformation. Under a coordinate transformation, where you start with some coordinates w plus minus or rather y plus minus to w plus minus is a function of y plus minus. Here I mean the plus goes to plus. Then the stress tensor transforms in the following way. Okay. Here I'm emphasizing two things. That under a Weyl transformation, this is how the stress tensor transforms. But under a coordinate transformation, it just transforms as a tensor. Okay? But if you are doing a coordinate plus Weyl, by that I mean, suppose you go from the y plus, let's say you had the flat metric in y, okay? And then you go to the flat metric in w, okay? Which in terms of the y's is a conformal transformation, or is a Weyl transformation. I'm using Weyl and conformal interchangeably. Then what happens is that the stress tensor transforms in the following way. I'm going to write it here. So plus C, so this is the vector part of the transformation, plus the anomalous part, sorry, 24, times the Schwartzian between W plus and Y plus. Okay? This is the Schwartzian derivative of W plus in terms of Y plus. I guess I can write it down, I can write down what it is. At least if I remember, it's W double prime over Y, W double prime over W prime prime minus 1/2 of W double prime over W prime squared. I think I got that right. Okay, so this is a Weyl transformation, this is a coordinate transformation, and this is a coordinate plus Weyl transformation. This thing follows from the things that I wrote down there. Okay, so why is this important? Because now we can be more precise about what we mean by having transparent boundary conditions. Okay.
What is the wild part of it, like in the last
the vial is the thing that gives you this term. Because under a vial transformation,
I mean,
T-
how do you identify the omega for this last?
oh, good question. Good.
I see.
This thing, where is it? Yeah, so this thing is equal to, dw by dy.
Oh, you have another omega square.
Yeah. And dy minus dy plus. So this is omega.
Oh, I see.
Okay? Let's just focus on the right exterior of the black hole and the flat space region. That looks something like this. Okay, this is the black hole side, and this is the flat space side. Remember that we are going to focus on vacuum solutions of the gravity region, which means that T, y plus on the ADS2 metric is equal to 0. It's a vacuum solution. Let me see. So here we have ADS2. Here we have flat. We're trying to determine what the stress tensor should be in the flat region. And the way I want to do it is I want to have transparent boundary conditions. The definition of that is going to be that when I do a vial transformation to remove the ADS2 part here, that's going to mean that I have a non-zero stress tensor here. And it's that stress tensor which freely flows into the flat space region. Okay? So the first step is this. So this is step number 1. Step number 2 is to do a vial transformation to take this space-time to this space-time, which is just flat everywhere. As a result of this vial transformation, T, y plus, in this region, flat, is going to be non-zero. It's going to be equal to, in fact, C over 12 pi over beta squared. And then step number 3 is to say that this stress tensor is the same everywhere, okay? even in the flat space region. So T, well, everywhere.
Yeah. You want to find certain of the tensor on the flat patch such that it would be 0 on the ADS part?
Exactly. You can think of it like that. Because we want to only focus, or to focus only on eternal black holes, which have zero stress tensor with the ADS2 metric. So now we're asking, what stress tensor should I put in the flat space region in order to support that eternal black hole? And we're doing it by going through this route.
So this is creating the heat back that keeps the thermal
Correct. So the picture now is,
if you had less, it's just that if you couple them with less, more,
mhm.
then would it be flow inward or outward?
Yeah, so if you choose a temperature here, which is, suppose here you had a black hole with some temperature T, a slightly smaller temperature, then it's going to the positive stress energy is going to come out in the flat space region until the temperature of this black hole goes down. And vice versa. Exactly. This is in this sense, this is different from a flat space black hole. So this has positive specific heat. What I said would not, wouldn't hold for Schwarzschild. Yeah. Right, for Schwarzschild, if you, yeah, because, let me see. Yeah, so what I was saying to David is that the Schwarzschild black hole has negative specific heat. Smaller black holes have higher temperature. Okay? So this means that that's why the eternal black hole, asymptotically flat eternal black hole is not thermodynamically stable, because a small fluctuation that decreases the temperature outside would cause the black hole to would cause just a runaway process, where the black hole is going to first lose some extra energy to the outside, and so get hotter, and then it's just going to continue to get hotter and hotter and hotter and shrink all the way down to zero.
So the other question, what do these transparent boundary conditions translate in the dual picture to the conditions of the quantum
Yeah, it's not clear. It's not clear. It's most easily constructed in the gravity picture.
Yeah.
Yeah.
Should have a clue.
It's a very special thing. So I don't know what is, so here there was a condition that we said that the CFT here is equal to the CFT there. Okay? That's one condition. I don't know what that corresponds to here in terms of what kind of, I don't know, fermions here that interact in the right way with SLK fermions. But that being said, people have considered situations where you impose some partially reflective boundary conditions, and the same story goes through. Like it's not a drastic difference. So that would correspond to something a bit more generic here. Okay. Okay, so this is what I mean by transparent boundary conditions. Okay. Right. My next topic was going to be on black hole thermodynamics. How much time do I have?
20 minutes.
Okay, that's good.
Can you explain again how they're going to translate to stable heat?
Yes. From step 2 to step 3. So we're saying that we have, so this line is an imaginary line. So far here I have this stress energy. Okay? This is stress energy plus plus. I don't know if that corresponds to right movers or left movers. I forget which one. So let's say it's the right movers. So they're going this way. They're just going to go through this boundary to here. So the right moving stress tensor here determines the right moving stress tensor here. So now the statement is that, well, we now know the answer to the question of what is the stress tensor is on the bath side in order to support the eternal black hole in the gravity side. Yeah. Can answer the question. Okay. All right. Okay. So we said various things about, well, the black hole evaporating and so on and so forth. So another twist to this, the thermodynamic instability of the eternal black hole is that if you suddenly have a fluctuation of higher temperature outside, that goes into the black hole, making it slightly bigger, which makes its temperature slightly lower, and so it's just going to consume all of the radiation coming in and get infinitely large. In that sense, that's why black holes in ADS are much better behaved. Okay, so black hole thermodynamics.
Can you repeat that statement about the holes in ADS?
So black holes in ADS have positive specific heat. Yeah, of course. Sorry, thank you so much. The reason why I didn't make that specification is that in EDS2 there is no distinction. You only have large black holes. But yeah, so in higher dimensions you have large black holes in EDS have positive specific heat. So you don't have this stability. You don't have this instability. Okay. Was it clear now? Yeah. Okay. Okay. So let's define a partition function. So the partition function is for gravity. You want to do this for gravity. So the definition is e to the minus beta tilde h. I'm calling my temperature beta tilde, inverse temperature beta tilde. The proposal for computing this quantity in gravity, first suggested by Gary Gibbons and Stephen Hawking, is to evaluate the Euclidean gravity path integral. Well, so far this is just a Euclidean path integral. There's no gravity here. This for these two lines. Euclidean because there's no I. And the proposal for gravity is to evaluate the gravitational path integral on the so-called Euclidean black hole. Here I'm not being, so generally speaking, you have to evaluate the gravity path integral with a boundary condition of having a circle, Euclidean circle at infinity of length beta. But now I just want to talk about the partition function for the black hole. And so you just have to evaluate the path integral on the Euclidean black hole solution, meaning that you're looking at a saddle point of the gravity path integral, and it's some e to the minus I classical. Okay. Given this path integral, or rather this contribution to the path integral, so this is something that depends on beta, on the specific solution, you can extract a thermal entropy. By the relation S thermal equals 1 minus beta tilde d beta tilde, derivative, respect to beta tilde, of log z, which is equal to 1 minus beta tilde d beta tilde of I jt on the Euclidean black hole solution. So this is what we're going to analyze. Okay? So we want to study the thermodynamics, or in this case, just extract the thermal entropy of the eternal black hole that we've been talking about. And this is the way to do it, is to take the solution and plug it in there. So the space-time, well, we want to now find the solution for the Euclidean black hole. It's, so the starting point, let's say, is the Lorentzian one. If you take the metric, well, let's imagine, so to get the Euclidean black hole from the Lorentzian one is you consider a slice with Z2 reflection symmetry, say this slice here, and then you take the metric and you continue the time variable to I times the time variable. And when you do that, you get this lower half here becomes something like this. Where here you have flat space. Here you have Euclidean ADS2 for the Euclidean black hole, plus, well, that's what it is. And there's we don't need to care about the CFT for now. If you can extend this solution to, well, you can extend the Euclidean solution, and what it looks like is just a reflection of what we just drew. Looks like this. And this is the famous cigar geometry, although right now it doesn't look like a cigar. It's a cigar if you, well, it's like this. You can draw the same picture like this, where this point here is the tip of the cigar. Okay? So this is called the Euclidean cigar.
So here everything beyond the point over there is ADS. Everything beyond the line.
Yes. So here's ADS, and here's flat space. Okay. Okay. What do I want to do? Okay. Let me see. How am I doing in time now?
If you want, you can stop here and give 10 minutes questions.
Okay.
It's up to you.
Okay.
So is this cigar smooth?
This cigar has the same, let's say, deficiencies as the Lorentzian spacetime had, in the sense that there's a delta function stress energy at the interface. And then it's a symbol. As in the metric is ADS2 here and flat here, and so on and so forth. The stress tensor here is not 0, and here it's 0, etc. Let me see. Can end with a punchline.
The time coordinate that you continued is the external?
Yes, exactly. The exterior time coordinate, so which did that, in this case goes around the cigar. Okay. The last thing. Okay, let me just say the following. The solution, the metric looks something like this. Okay? Let's imagine that we let's imagine we take this solution. It's not going to be clear why I'm doing this, but let's just do it for now. And we impose the following periodicity for tau. We take tau to go as tau plus beta tilde. Okay? In this case, let's take this metric and let's focus on the region near the tip. The metric near the tip is going to be just flat space, right? Because this is a Riemannian geometry. If you look locally near any point, it's flat space, and it looks something like this. Well, just flat space, so it's going to be dr squared plus r squared. R is just some coordinate times 2 pi tau over beta. Oh, sorry, d of this. 2 pi d tau squared. Okay? Let's define all of this as d tau hat. Notice that because tau is identified with tau plus beta tilde, this means that tau hat is identified with tau hat plus.
Beta and beta tilde are the same.
No, that's important here. I'm saying so. I'm considering a black hole solution with inverse temperature beta, but I'm going to impose that the metric has periodicity beta tilde. Okay? This is going to be important later, but for now, this is just to just as a warm up. The periodicity of tau hat is going to be 2 pi times beta tilde over beta.
Sorry, I have a question.
Yes.
Where exactly did beta enter this branch diagram? Beta tilde is fine, but beta itself, where?
We are plugging in the solution with inverse temperature beta. I guess maybe I need to add more labels here. I went too quick here. There's a beta tilde parameter that comes from this, and we're plugging in the solution with temperature beta. Okay?
Because it's a saddle point of this integral.
For now, well, the saddle point is when beta is equal to beta tilde. Okay, so
Or we just plug it?
yeah, but for now, just
So in Gibbons Hawking there were no beta tildes.
I agree. In Gibbons-Hawking, there's just one beta, and that picks out the solution with a black hole with inverse temperature beta. I just wanted to end with the following picture that if you consider a solution with inverse temperature beta, and you just impose by hand that the periodicity is with beta tilde, then what you find is that there's a conical singularity at the tip. Okay? There's going to be a conical singularity here if the black hole is of temperature beta, but the periodicity is of beta tilde. Okay? I just wanted to make this point. And I'm going to use this point next time to derive the entropy. Any questions?
You use iClassical and then you change to IJT after you took that. So are they the same?
Yeah, so this statement here was all general. For any, you have your favorite gravitational theory, you plug in the classical solution into the classical solution of the equations of motion back into the action. That's how you derive Z. Okay, the on-shell partition function, or path integral. Now we are considering, we want to apply this to the eternal black hole in JT gravity. So now we're specializing. Okay? And I'm only focusing on the contribution coming from the gravity part of the action. In principle, there's also the CFD part, but that is subleading. But,
So this is the Gibbons-Hawking prescription.
yes,
We're doing the leading semi-classical calculation.
that is correct.
In general, of course, there would be a sum over such.
Indeed,
But you're not arguing with that at this point,
correct.
until you get to replicate.
Yes. This is meant to be, so this is actually not the way that it's usually presented. Well, the computational thermal entropy is not usually presented in this way, but I'm going to show that there's a trick of doing this, just choosing the wrong temperature and so on, where you can compute the thermal entropy by picking just the contribution from the conical singularity. Okay?
Do we have control over the fluctuations around the saddle point? Like, do we know like what it means in a gravitational fluctuating integral will be positive, negative, zero modes?
I mean, it depends on the model. Here, those fluctuations are going to be suppressed by G Newton. Or at least their size compared to the classical contribution.
What is the relation between the cigar geometry and the previous?
Um,
Like
this-
a lot of layers in the previous picture.
These two pictures are the same. The cigar geometry is just a Euclidean continuation of the Lorentzian geometry.
So
So-
this is a Lorentzian.
No, so these are both Euclidean. This is the Euclidean metric. If you take tau to I times t, then you get minus dt squared. This is the Lorentzian spacetime. But I was doing it more diagrammatically. But yeah.
We forgot to thank you immediately
Okay.
afterwards. If there is one more question, we can thank you, the speaker, again. Do you want one more question? No. Okay, we thank you again.
In high dimension, the same transparent boundary condition does not allow the probability of predictability.
It's not, we don't have this trick of the vial, the stress tensor does not transform in a simple way, as in 2 dimensions. So here we define transparent boundary conditions by first transforming the bulk to flat space, and then we know what the stress tensor is there, and then we say it's the same stress tensor that's going to also be in the flat space in the batch. Yeah, we don't have similar construction in higher dimensions. There, the most, well, there you can use holography, ADS-CFT, to get something similar. But that's another kind of idea.
Yeah, half an hour break, we meet again. It's 3 o'clock.